Hi everyone, good evening. This is Shefali Singla, and in today's session, we will be learning the concept of floating point representation. So, in Unit 2, we have a concept of fixed and floating point representation. तो काफी सारे स्टूडेंट्स काफी टाइम से बोल रहे थे कि मैम फ्लोटिंग पॉइंट वाले फॉर्मेट्स में कंफ्यूजन होती है, प्रॉब्लम होती है. सो वी विल बी लर्निंग द कॉन्सेप्ट्स ऑफ फ्लोटिंग पॉइंट रिप्रेजेंटेशन इन टुडेज सेशन एंड डेफिनेटली फ्लोटिंग पॉइंट रिप्रेजेंटेशन के बेसिस पे जो क्वेश्चंस होंगे वो आज वाली मास्टर क्लास में हम लोग डिस्कस करेंगे. सो if you want to join the master class, you can refer to the link which is given in the description box. And apart from that, you can also join the telegram group जहाँ पे सारी classes के links share होते हैं. Okay, तो floating point representation की बात शुरू करते हैं without wasting any time. So first of all, हम floating point numbers को store क्यों करते हैं? Why we need a special format to store the floating point numbers? कई बार रियल लाइफ में हम कुछ ऐसे नंबर्स के साथ डील करते हैं जो साइज में काफी ज्यादा बड़े होते हैं या फिर काफी ज्यादा छोटे होते हैं. फॉर एग्जांपल, अगर आप स्क्रीन पे देख सकते हैं, यहाँ पे मैंने दो नंबर्स लिए हैं. द फर्स्ट नंबर इज टू बिग, इट्स 9670000, so it's difficult to read, it's difficult to find out its value. Similarly, second number is too small, this is a very small fraction, so this number is too large, and the second number is it's too small. तो हम क्या चाहते हैं कि नंबर को कुछ इस फॉर्मेट में डलवाओ, इस फॉर्मेट में लिखो कि आपको नंबर को अंडरस्टैंड करना, रीड करना इजी हो. So in that scenario, we need the floating point numbers. Moreover, in order to store this number, a large memory is required. तो जब आप इसको compact form में represent करोगे तो definitely the requirement of the memory to save these numbers will be less. तो इस नंबर को हम कैसे लिख सकते हैं? Like here we have the zeros and there is no decimal. So we can form the decimal. We know that if somewhere it's written like 100, तो क्या मैं 100 को 100.0 लिख सकती हूँ? Definitely yes, यानी कि 100 के बाद आप decimal consider कर सकते हैं. Now I want to write it in a readable format. तो हम क्या करेंगे? I'll move this decimal towards the left. कितना left move करना है? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I'm moving this decimal by 13 places. So after moving the decimal, I can write this as 9.67 into 10 raised to power. कितना मूव किया है? 13. 13 लेफ्ट गए हैं तो पावर विल बी प्लस 13. This is plus 13. Why am I writing plus 13? Because हमें मालूम है जब आप किसी भी नंबर को लेते हैं, so I can write this as 96700, जो भी आपके पास वैल्यू दी गई है, I can multiply this number with 10 raised to power 13 and divide this number by 10 raised to power 13. माइनस में पावर आ गई, दिस इज इन प्लस. तो इसका मतलब क्या कि अगर आपके पास माइनस में पावर है तो वैल्यू डिनोमिनेटर में चली जाएगी, एंड इफ इट्स गोइंग टू डिनोमिनेटर तो दीज टू वैल्यूज विल बी कैंसल आउट, तो आपके पास ओरिजिनल नंबर आ रहा है. Now, when the power is in negative, that means I'm dividing the given number by 10 raised to power minus 13. तो आपके पास decimal move हो गया. So this is the the special format in which we have the mantissa, we have the exponent, and definitely we know that numbers can be positive or negative. So we need to take here the sign. This is the positive sign. As we already know that अगर आपके पास number positive होता है, in order to represent positive or negative number, we use one bit. क्योंकि दो ही options है, so that bit is known as the sign bit. So if the number is positive number, then we represent it with a bit that is 0. If the number is negative, then we use the bit 1. Okay, so since here the given number is positive, so that's why I'm taking here positive. But जब हम इसको fraction में स्टोर करवाएंगे, हम फ्लोटिंग पॉइंट फॉर्मेट में स्टोर करवाएंगे, तो डेफिनेटली वी विल बी हैविंग द बिट वैल्यू एज 0. इतना क्लियर हुआ? नाउ इफ वी टॉक अबाउट द सेकंड नंबर, दिस नंबर इज टू स्मॉल, तो यहाँ पे क्या कर सकते हैं, वी कैन मूव दिस डेसिमल बाय हाउ मेनी प्लेसेस, लेट्स काउंट द zeros, 2, 3, 4, 5, 6, 7, 8, 9, 10. This means that I can multiply it with 10 into 10 raised to power minus 10. अब आपको multiply करवाना है, that means we'll be using this value. So here we'll get number is positive 9.67 into 10 raised to power minus 10. Make sense? So these are the two formats, these are the two ways where you can write the number. So अगर हम इसको generalize करते हैं, then here we can have the sign of the number. It can be positive or negative. Now after that we have the mantissa part. We are given with the mantissa. Then we have some base, और base की कुछ ना कुछ पार होगी. This is known as the exponent. Plus minus e, that is the exponent. So this is nothing but this is the format for the floating point representation, where we need to know the value of mantissa, bias and exponent, where m is representing mantissa, b is representing biased and e is representing exponent. जब हम exponent की बात करेंगे, I'll be using two terms, actual exponent and biased exponent. Actual exponent होता है when you have the mantissa in the normalized format, तो उस टाइम पे जो actual exponent होता है, that is the value of AE, actual exponent. Biased exponent हम calculate करते हैं by adding the bias and the actual exponent. हो सकता है कुछ लोगों के लिए alien terms हो, but don't worry, I'll be discussing all these points in detail. As of now, have you understood why are we using the floating point representation? So this is the special format which is used to represent the very large number of very small numbers with the limited memory space. So to represent the above numbers with the limited memory space, there is a need of the special format, and this is that special format. Now, as we have already defined that here we have to identify the value of mantissa, sign and exponent. So if I talk about the general format, and we are storing the number in the floating point formats, we do have single precision and double precision. Single precision is 32-bit format and double precision is 64-bit format. तो जब आपके पास ये single या double precision format आता है, we have three fields here. From the number, what all things do we need to represent? Anyhow, जब हम by base लेंगे, तो obviously for the binary numbers it's 2, so we need not to specify that, but definitely we need to specify the sign bit for the number. So this is the sign bit. Sign bit. Then we need to store the biased exponent, and the third field is known as the mantissa. There are some conditions for finding the mantissa and biased exponent. Biased exponent is nothing but that is bias plus actual exponent. In while we will be discussing that what is or how to calculate bias. And mantissa should always be in the normalized format. It should always be in the normalized format. इतना क्लियर है? एक बार फटाफट से कंफर्मेशन दे दीजिए. Now let's talk about these fields in more detail. So the floating point number is stored in the memory with the three fields. Order बताया, पहले sign आएगा, फिर biased exponent आएगा, and then we'll be having the mantissa field. So first field is the sign field. Sign field हमेशा सिर्फ और सिर्फ नंबर का साइन रिप्रेजेंट करेगी जो पॉजिटिव या नेगेटिव हो सकता है, इसलिए जो साइन फील्ड होता है इसका साइज हमेशा फिक्स्ड होता है. इट रियली डजंट मैटर वेदर यू आर यूजिंग द 16 बिट फॉर्मेट, 32 बिट फॉर्मेट और 64 बिट फॉर्मेट. साइन फील्ड का जो साइज है दैट विल ऑलवेज बी 1 bit. As I have already defined, for positive numbers it will be 0 and for negative numbers it will be 1. Tally field clear? Negative is 1. Then we have the biased exponent field. Here the biased value is depending on the floating point format size of the exponent field. अब जो आपके पास 16 bit format होता है, for 16 bit format biased exponent field is of 5 bits. 16 bit format में this is of 5 bits. For biased exponent, we have 5 bits. If it's 32-bit format, then in that case, 8 bits are taken by bit format. So 8 bits are required for biased exponent. And in double precision, that is 64-bit format, we have 11 bits. Format, we have 11 bits for biased exponent field. Now, the value of the bias is always based on the size of the biased exponent field. So, biased exponent के लिए हमें bias calculate करना है because biased exponent, I'm writing this as BE, biased exponent, BE, this is equal to bias plus actual exponent. Actual exponent. Okay, now what will be the bias? First of all, let's recall the range for 2's complement. The range for 2's complement was minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1. Correct? This was the range for 2's complement. So, जब हम bias return करते हैं, it is returned as 2 raised to power n minus 1 minus 1. That means if the bias is taking 5 bits, if the biased exponent field is taking 5 bits, तो आपके पास bias होगा, bias will be 2 raised to power 5 minus 1 minus 1. That is 2 raised to power 4, 16 minus 1 is 15, so it will be 15. Okay. Similarly, if I write here more examples, let's say we have some hypothetical format given to you and the biased exponent field, biased exponent field size को मैं represent कर रही हूँ n के साथ. So this is, if it's 5, then we know that bias comes out to be n 2 raised to power 5 minus 1 minus 1. So we have already calculated this. It is 15. If for any hypothetical system, if the biased exponent field size is 6 bits, अगर आपके पास 6 bits है, then the bias will be 2 raised to power 6 minus 1 minus 1. It comes out to be 31. If it is of 7 bits, biased exponent field का size 7 bits दिया गया है, तो आपके पास bias calculate होगा 2 raised to power 7 minus 1 minus 1. So it is 128, 2 raised to power 6 is 64. 64 minus 1 is 63. Then if n is equal to 8, then it will be 2 raised to power 8 minus 1, 7. 128 minus 1 is 127. So in general, we can say that bias is nothing but that is calculated as 2 raised to power n minus 1 minus 1, where n represents the size of the biased exponent field, where n represents the size of biased exponent field. Is it clear? So calculation of biased is very important. You should know that how to calculate bias, because जब भी आप number को store करवाते हो in the normalized format, in the floating point representation, तो भी आपको bias calculate करना है. आपको या तो biased exponent given होगा या actual exponent पता होगा. So bias हमेशा और हमेशा आपको find करना पड़ेगा. So this is the formula to calculate bias. Are you all comfortable with biased exponent field and bias? So have you understood that how to get the value of biased exponent? So biased exponent is nothing but, I'm again going to the previous slide. So biased exponent is nothing but this is equal to the bias. Now you know that how to calculate the bias plus actual exponent. ये इतना clear हुआ? Now we have the third field of the format, that is the Mentisa. So for the Mentisa, we need to have the Mentisa in the normalized format. Okay. So third field is the Mentisa or the significant. The floating point number is always stored in the memory with the normalized Mentisa. हमेशा और हमेशा number आपके पास normalized Mentisa में store होगा. Normalized Mentisa क्या बोलते हैं कि जब भी आप number को store करते हो तो decimal से पहले आपके पास सिर्फ एक ही bit होनी चाहिए and that should be 1. उसके बाद decimal के बाद आपके पास जो मर्जी bit हो सकती है. B is basically representing the bit, so it can be 0 or 1. That means, again I'm repeating this point, बहुत सारे students यहाँ पे गलती करते हैं. Normalized Mentisa का मतलब ये है कि decimal से पहले आपके पास एक ही bit होनी चाहिए and that must be 1. This is always 1. This is fixed according to the normalized Mentisa. So these bits can be anything. It can be any combination of 0 and 1. अगर मान लीजिए जो आपको नंबर दिया गया है वो इस फॉर्मेट में नहीं है, नॉर्मलाइज्ड मेंटिसा नहीं है, देन इन दैट केस वी नीड टू एडजस्ट द डेसिमल. आप डेसिमल को मूव करवाओगे लेफ्ट या राइट. अभी हमने फर्स्ट स्लाइड में समझा कि डेसिमल को कैसे मूव करवाते. सो बाय मूविंग द डेसिमल टू लेफ्ट और राइट यू हैव टू गेट द मेंटिसा इन द नॉर्मलाइज्ड मेंटिसा फॉर्मेट. So if the given number is not in the normalized format, either by increasing or decreasing, किसको increase या decrease करोगे? Exponent value को to convert the number in the normalized format. तो जब आपके पास नॉर्मलाइज फॉर्मेट में आ गया, हर मेंटिसा में हमें ये पता है कि डेसिमल से पहले एक ही बिट होगी एंड दैट विल बी 1. सो डेफिनेटली वी नीड नॉट टू स्टोर दैट इन द मेमोरी. बाय डिफॉल्ट आपके पास अगर मान लीजिए मेंटिसा की बिट्स 23 है तो बाय डिफॉल्ट इट मींस दैट इट इज 24 बिकॉज वी आर नॉट स्टोरिंग वन बिट. क्योंकि जब स्टोर करने के टाइम पे हम 1 को स्टोर नहीं करवा रहे तो ऑब्वियसली बात है कि रिट्रीवल के टाइम पे भी आपको सिर्फ डेसिमल के बाद वाली बिट्स मिलेंगी, डेसिमल से पहले वाला 1 नहीं मिलेगा. So when the number is in the normalized format, before the decimal point, the digit is always 1. हमेशा decimal से पहले वाला जो digit होगा, that will always be 1. So there is no need to store the bit in the memory. So I'm highlighting this point and let me highlight this always 1. Decimal से पहले जो digit होगा that will always be 1. It is not simply saying that कि decimal से पहले एक ही digit होना चाहिए, ये बोल रहे हैं कि एक ही digit होना चाहिए and that must be 1. मैं इस पॉइंट पे बार बार इसलिए स्ट्रेस दे रही हूँ क्योंकि बहुत बार स्टूडेंट्स इस पॉइंट को स्किप कर देते हैं. सो प्लीज टेक केयर ऑफ दिस पॉइंट. ओके. Now let's consider one example. If I'm saying that we have the number 1.111.011 into 2, this is in the binary, so base is 2, and let's say the power is अब जो मैं पावर लिख रही हूँ ये भी किस में लिख रही हूँ, सब कुछ मैं बाइनरी में लिख रही हूँ. सो इफ आई एम राइटिंग 011, 011 इज नथिंग बट दिस इज द बाइनरी ऑफ 3. इज इट इन द नॉर्मलाइज्ड फॉर्मेट? जो नंबर दिया गया है क्या ये नॉर्मलाइज्ड फॉर्मेट में? अभी हमने डिस्कशन की कि भाई डेसिमल से पहले हमारे पास एक ही डिजिट होना चाहिए एंड दैट मस्ट बी 1. सो वी कैन से दैट दिस इज not normalized because before the decimal we have 3 digits and some bits are there, so it is not normalized. So what should I do now? I need to move this decimal. कितना मूव करेंगे? बाय हाउ मेनी प्लेसेस? 1 and 2. लेफ्ट साइड जा रहे हैं यानी कि आप नंबर को छोटा कर रहे हो, सो दैट मीन्स यू आर डिवाइडिंग द नंबर बाय हाउ मच? 2. तो आई कैन राइट दिस एज 1.11011. ये डेसिमल को मैंने मूव करवा दिया एंड हियर यू हैड 2 raised to power 011. ये माइनस वाली पार की वजह से लेफ्ट में मूव हो गए, सो प्लस 2. व्हाट इज 2? दैट इज 10. आप 10 लिख दो या फिर मैंने ये किसका बाइनरी लिए? 2 का. सो 3 plus 2 is nothing but 5. So I can write this number as 11011 into 2 raised to power 101, that is 5. Is this clear? So we have talked about all the 3 fields. Anyone having any doubt? Let me take here one more example. If I'm given with the number 0.001011 into 2 raised to power 101. Now, this number is not in the normalized format. तो क्या करना पड़ेगा? We need to move this decimal. डेसिमल से पहले हमें एक 1 चाहिए, तो दिस विल गिव यू द हिंट कि कितना मूव करना है. वी हैव टू मूव इट बाय 3 प्लेसेस. सो दिस बिकम्स 1.011 into 2 raised to power 101. तो ऑलरेडी पावर में था. अब आपने राइट साइड मूव करवाया यानी कि प्लस करवाया है, सो माइनस. क्योंकि ऑलरेडी राइट साइड पे मूव किया है तो यहाँ पे 2 raised to power कितनी प्लेसेस से? 3. This is the binary of 3. Simplify it. 5 minus 3 is 2. So it comes out to be 1.011 into 2 raised to power 010. That is 2. Make sense? Guys, is this clear? Now, whatever power you have, अब आपके पास numbers जब आपने normalized मेंटीसा को normalize कर दिया, अब उसके बाद जो resultant आपके पास power आ रही है, for example, this was the normalized format for this example, and this is the normalized result or normalized mentisa for this one. So now whatever is the power, जो भी यहाँ पे power आ रही है, that is nothing but that is your actual exponent. Similarly here, whatever is in the power, that is your actual exponent. बायस हमें कैलकुलेट करना आता है. एक्चुअल एक्सपोनेंट हमें पता है कि जो नॉर्मलाइज्ड मेंटीसा में आपके पास पावर में होगा, दैट विल बी द एक्चुअल एक्सपोनेंट. जस्ट add them both and you will get the value of the biased exponent. Okay, so this is about all the 3 fields. Let's discuss one question for more clarity. Now let's assume that we are given that we have to show the storage format of the following number in the memory. यहाँ पे आपको format दिया गया है कि 1 bit आपके पास साइन के लिए यूज हो रही है, 5 bits biased exponent के लिए and 10 bits are being used for the mentisa. And you were given with the number which is, as of now, obviously you can see that this is not in the normalized format. Number is given as plus, मैं थोड़ा सा बड़ा करके लिख रही हूँ, 4 ones 01.11 into 2 raised to power plus 010. 010 is nothing but that's the binary of 2. Now this is the given number is not in the normalized format. So first of all, we need to normalize it. We'll get the value of actual exponent and we'll calculate the bias. Bias को हमेशा और हमेशा हम biased exponent के basis पे calculate करते हैं. So हमें क्या represent करना है? हमें storage format दिखाना है. So let me draw the format first. We know that in the format we have 3 fields. First one is the sign. 3 fields are there. अगर यहाँ तक कोई डाउट है तो बेटा आप पूछ सकते हो, बाकी आई होप कि जब हम ये क्वेश्चन कर लेंगे आपको और क्लैरिटी आ जाएगी. सो वी हैव द साइन, biased exponent and Mentisa. This is for sine, biased exponent, and then we have Mentisa. Okay, so here the size of each field is given in the question itself. That is, the sign bit is using 1 bit, 1 bit, biased exponent 5 bits, and Mentisa will be using 10 bits. So basically you are given with the 16-bit format. Now, here the number is positive. Positive means, since the number is positive, positive means sign bit will be 0. So I'll write here 0. एक ही bit store करवानी थी. Biased exponent के लिए हमें bias calculate करवाना पड़ेगा. Biased exponent is nothing but that is the actual exponent plus bias. Bias plus actual exponent. Bias क्या होगा? If we have 5 bits, so we can calculate this. Bias will be, we have discussed the formula, it's 2 raised to power n minus 1, 2 raised to power 5 minus 1 minus 1. So this comes out to be 15. So bias will be 15. For actual exponent, first of all, we need to have this number in the normalized format. So here, before decimal, so many bits are there. We just want 1 bit and that must be 1. हमें decimal से पहले एक ही bit चाहिए और वो भी 1 होनी चाहिए. तो we need to move this decimal. हमें इस decimal को move करना पड़ेगा by how many bits? 1, 2, 3, 4, 5. That means it comes out to be 1.1110111 into 2 raised to power. Already आपके पास 0, 1, 0 तो था ही और हमने कितनी positions के साथ move करवाया इसको? 5 places. So it is 5. 5 is nothing but 101. This is the binary of 5. So ultimately this comes out to be 1.1110111 into 2 raised to power 5 plus 2 is 7. 7 is nothing but 111. Correct? तो ये obviously आपके पास power plus में आ रही है. So what is the actual exponent? Here we can see that the actual exponent is nothing but that is 7. 15 plus 7 is 22. Now anyhow we have to return everything in the binary form. So 22 is nothing but the binary of 22 is 16. 8 वाली term नहीं आएगी and 4, 16 plus 4 is 20, 2 and 0. So this comes out to be biased exponent is nothing but this is 10110. So it is 10110. Do we need to add extra zeros? No, because आपको 5 bits ही store करवानी थी and for the biased exponent we are getting 5 bits. Now this is in the normalized format. We need to store the Mentisa. हमने ये बोला है कि normalized format में हमेशा decimal से पहले आपके पास single one आएगा. So we need not to store that one. तो Mentisa में आपके पास सिर्फ और सिर्फ decimal के बाद वाली bits store होंगी. So Mentisa will be 1110111 and after that we have to store 10 bits. आपके पास 7 bits आ रही है. So we will be adding here 3 zeros. So this is the required storage format for the given number in 16-bit format. कई बार क्वेश्चन में आपको फॉर्मेट और फील्ड्स का साइज गिवन नहीं होता है. सो डिपेंडिंग ऑन द फॉर्मेट, बिकॉज IEEE has defined two formats. One is for single precision, that is 32-bit, and other one is double precision with the size 64 bits. So let's identify the size. So the floating point numbers are always represented by using the IEEE standard. IEEE standard 754 defines the two types of floating point numbers, single precision that is 32-bit floating point and double precision that is 64-bit. जैसे हमने जो पिछला एग्जांपल लिया उसमें टोटल बिट्स आपके पास 16 बिट्स स्टोर हो रही है, but in single precision will be having 32 bits. If we look at the format, so definitely there will be 3 fields. कोई भी फॉर्मेट है आपके पास fields 3 ही रहेंगी, सिर्फ और सिर्फ उन fields के साइज में डिफरेंस आएगा. और कौन सी field के साइज में डिफरेंस आएगा? It will be the biased exponent and the Mantissa field, because sign bit is not going to change. Sign bit हमेशा आपके पास एक ही bit use होगी. Similarly here, let me draw it for double precision. So we have 3 fields here. So this is for sign, or let me write it inside the box. Sign bit. For sign bit, be it 32-bit format, or let me write here 32-bit format, and here we have 64-bit format. Okay, so sign bit is always going to take how many bits? काम करने का तरीका सब में सेम है, सिर्फ और सिर्फ बिट्स में डिफरेंस आएगा. So here this will be using 1 bit. For sign, obviously we need 1 bit. 1 bit. Here also it will be using 1 bit. For 32-bit, the biased exponent is of size 8 bits. Now, 32 minus 8 is 24 minus 1. Total आपको third field की bits find करनी है. So 32 minus 1 minus 8. So that is returning 23 bits. Similarly, in 64-bit, we have 11 bits used for the biased exponent, and for the Mantissa, remaining bits will be 64 minus 12 is 52 bits. I hope that these formats are clear. So this is for biased exponent. And here we have Mantissa. Similarly, here we have biased exponent. And here we have Mantissa. So this is about the different formats. I hope that this is clear to everyone. Can you please write in the chat section that what will be the bias for 32-bit? 32-bit के लिए bias क्या होगा? Bias will be, already we have calculated, it's 2 raised to power 8 minus 1 minus 1. 2 raised to power 7 is 128 minus 1. It comes out to be 127. If it is 64-bit, for 64-bit, bias will be 2 raised to power, यहाँ पे देखिए biased exponent का size कितना है, that is 11 bits, so it will be 2 raised to power 11 minus 1 minus 1. 2 raised to power 10 is 1024 minus 1 is 1023. This is the size. This is the bias for 64-bit, that is double precision floating point representation. I hope that this is clear to everyone. So this is the practice question. Just try it once after the class, because after this we have 1 hour break, and then we will be having the master class in which I will provide the solution of this question. So don't forget to join today's master class, because On the basis of the concepts that we have learned in this session, we will be solving the questions. आपको पता है हर मास्टर क्लास यूट्यूब सेशन से लिंक्ड है. जो भी कॉन्सेप्ट हम यूट्यूब में डिस्कस करते हैं उसके बेसिस पे इमीडिएटली आफ्टर 1 or 1.5 hour we have the master class. And if you want to cover the whole syllabus in detail, the way we are covering, obviously YouTube पे 100% completion तो नहीं हो पाएगी, because if I talk about the computer science, we have 10 units in paper 2. And those are obviously vast units, so we cannot cover the 100% syllabus on the YouTube, but I'm trying my best कि मैं maximum topics जो important है या जिसमें students को confusion होती है, problem होती है, वो मैं YouTube पे cover करूँ. But again, 100% completion won't be there. So if you want to cover the 100% syllabus in detail in the live sessions, then this batch is for you. We have launched UGC NET December 2024 Foundation Batch 2.0. So in this batch, we will be covering the whole syllabus of paper 1 and paper 2 in the live classes, जो बेस्ड होंगी लेटेस्ट एग्जाम पैटर्न और जो recent syllabus है उसके अकॉर्डिंग. And these classes will be available in the English. There are few branches for which we have completely English batches as well, but as of now for computer science we just have the classes in the English. So including the live classes, you will get here the structured study notes and the practice questions, and definitely solve previous year papers, mock test series, everything will be included in this one. If I talk about the extra features, so special mentorship course for PhD admissions will be there. आप देख सकते हो पेपर 2 के लिए we have lot many options, but for physical education and Sanskrit, these sessions will be in the recorded format. But अगर आपकी branch computer science है, if you are, I'm assuming अगर आप ये topic देख रहे हो तो you are from computer science, so computer science के लिए बेटा हमारे पास live batch है. तो अगर by any chance आपका कोई live session miss हो जाता है तो आप उसकी recording देख सकते हो. And अगर doubt आता है, then you can ask your doubts in the live class, or you can post your queries on the dashboard. क्योंकि जब आपको link मिल जाएगा, credentials मिल जाएंगे, then you can post your doubts in the doubts and the discussion forum, and definitely within 4 hours you will get the response for all of your queries. Okay, so we have limited seats available. If you want to enroll yourself, quickly enroll yourself. Unnecessarily delay करने का कोई फायदा नहीं है. जो आपकी subscription होगी, that will be valid till the December examination. And if you are looking for the promo code, on the top of this slide I have provided the promo code. Use this code in order to get the discount. अगर आपकी कुछ भी doubts या queries हैं, you can send it on the Telegram group. So that is Shefali ma'am Testbook. And apart from that, don't forget to subscribe the channel. Lectures अच्छे लग रहे हैं, आप regularly join कर रहे हो, और कई बार मैम notification नहीं मिलता है, तो बेटा चैनल को सब्सक्राइब करके बेल आइकन को क्लिक कर दो, आपको नोटिफिकेशंस मिलने शुरू हो जाएंगे, उससे आपका कोई भी सेशन मिस नहीं होगा. ओके. And if you want to get to have more information related to the super coaching batch, क्या होता है, क्या course structure है, तो आप जब website पे जाएंगे, नीचे description box में links भी given है, so just explore those links, go to the course structure, वहाँ पे आपको completely course structure मिल जाएगा. Every day we are having 2 sessions in the super coaching. One session is in the morning and the other one is in the evening, and the duration of these sessions is 2 hours. तो हर एक session 2 hours का होता है, plus minus 5-10 minutes could be there. So one session is in the morning and second session is in the evening. And apart from that, we are covering the YouTube. We are covering the important topics on YouTube, and जो भी concept हम YouTube पे करते हैं उसके basis पे master class होती है. Timing for the free sessions, these are free sessions. बहुत सारे students को confusion होती है कि master class free है या paid है, क्योंकि Testbook platform पे है तो it will be paid. No, master classes are free. So if I talk about the free sessions, we have the sessions on YouTube and master class. Timing is 6:30 p.m. and for master classes it is 8:30 p.m. On the same day, instead of keeping weekends off, I'm taking off on Thursdays and Fridays. So Thursday and Fridays are off. उसके अलावा वीक में हम 5 दिन मिलते हैं, but definitely tomorrow is Raksha Bandhan, so there will be a holiday on Raksha Bandhan. So I'll see you guys. This topic will be covered on Tuesday. So I'll see you guys on Tuesday. All right? Any doubts? Any concerns? Any questions? टेलीग्राम ग्रुप का लिंक दिया गया है, डिस्क्रिप्शन बॉक्स को भी एक्सप्लोर कर लीजिए. Channel name is on the top left corner and promo code is in the center, so whole information is there. If there are no queries, then we'll end our discussion here. This is all about this session. Thank you so much, guys. I'll see you in next session and hope to see you in the masterclass. Take care. Bye bye.